how to use MATLAB for image, at least pre-processing. So MATLAB has many functionalities, and basically it is designed for solving the problem of matrix rather than always writing for loops. MATLAB will automatically handle such kinds of things effectively and efficiently with minimum time. Images are also in a matrix form because they are a combination of pixels that are available in a two-dimensional space. Whatever matrix you have, you can solve it using MATLAB, Matrix Lab. For us, our major aim is manipulating images. So the first step in image is reading the image itself. So for reading the image, there is IMRead. For the different functionalities to work, you have to give it the current directory. Either you have to give it the directory when you are defining where to read, or else you have to change the current directory here. Now the image corpus in my PC are available in a folder image corpus, which is situated in the desktop. So once I give this one, it will refer from that, the image that I'm trying to manipulate. So don't forget defining the current directory. Once I define the current directory where the images are available, so I can start reading them. For reading images, we have to use IMRead. IM means image. Most of the functions are starts with IM. If there are functions designed for image manipulations, IMRead means reading the image. When we are reading the image, we are reading the content of the image. By looking at the content of the image, we can understand that whether the image is a monochrome image or a grayscale image or a color image. If I read the image called sample 0 BMP, the pixel elements are identified by IMRead and saved in a variable called image. If you see the values, they range from 0 up to 255. That means this image is a grayscale image. It's possible to change the grayscale image into binary image. One of the function is dithering. The other is image from binary to, from grayscale to binary. Mostly the dithering is working well for changing the grayscale image to binary. So there is a dither function that we can use. Given an image, our image is labeled with IMAGE. Then if we dither it, we'll get an image with zeros and ones. That means the image is converted into monochrome image. Now let's read the image itself and see what it looks like. For that, we need IMRead plus IMShow. IMRead is trying to read the content of the image and save it in variable IMAGE. Then initialize a figure with label 1 and then call ImShow, image show. Then give it the variable where we stored after reading the image content. Then we'll see what the image looks like. So the image is poor in quality, especially the background. Either we have to attempt to filter it without binarization, or else we have to filter it after binarization. Even if you want to challenge the filtering techniques, it's possible to add more noise. There are functions that we can use. Anyway, let's use first, given the image, if we apply median filtering. Median filtering has its own function, and it's considered as the best filtering techniques, especially to remove salt and pepper noise, and mostly noises that are corrupting our image are salt and pepper noise. So the name for median filtering is MEDFILT. 2 means in a 2-dimensional space. Give it an image, and then figure and ImShow is to display the result of median filtering. By default, median filtering is using a 3x3 window. If you want to change the window, you can add within a square bracket the windows that you want to use for identifying the median, which can replace a given pixel that we are considering. If you run it using a 5x5 window, this is the result. There are cuts here and there because it's evaluating using large space. But let's use a 3x3 window. It's possible to define 3x3, or else it's possible to remove this square bracket, since by default median filtering is using a 3x3 window. This one is better than the previous one because there is no cuts within the picture elements. But still the foreground pixel is not clear. One of the options that we have is we have to attempt to clear it using binarization by converting the grayscale image into binary. We converted into binary using dithering, and the monochrome image is saved in BW. Again, if we run it by opening another picture where to show the image, we'll get a better image. So the background is now clean because after dithering, the result of dithering is the picture elements are converted from grayscale to monochrome. Says that the picture elements are with value 0 and 1. So we have this kind of dithered monochrome image. And as per the monochrome image, some of the pixels are corrupting the original characters or words that are written within the image. And if you see the distribution of the pixels, especially the black pixels, they are forming a salt and a pepper noise. And such salt and pepper noises are easy for medium filtering to remove them. Because if we see around them, since they are appearing occasionally, they can be easily removed because around them, most of the pixels are with 0 values. There are Gaussian filtering, there are mean filtering. For mean filtering also we can use image filter. Even the windows that we need, we can create it automatically, like h is equal to, if you say once, a window with 3 by 3 value 1. We can create a window 5 by 5 once, or we can create a window with zeros. So depending on, especially for morphological analysis, we need them. Now also for mean filtering, we can minimize the way we are handling the image and removing any inconvenience by defining the window automatically and then run image filtering for mean. The code that we are using is IM filter. But IM filter is also used for running convolution correlation. But the default is IM filter for mean filtering or average filtering. Given window 1 by 1 in a 3 by 3, mask, then if using that, if the mean filtering is trying to identify the noises and remove them, then finally, given the original image, if we use median filtering, almost most of, even part of the original images are removed. So again, we have to optimize our window. Rather than using 111, we can convert those 11 into decimal numbers. Like if you divide them with 9, you will get 0.111. And if you run it again, a better image. Again, still, there are noises within the image. So to remove those noises, still we have to see a better optimal window. That means we have to change maybe the window size from 3 to 5. And then let's divide it with 25. Then use this 5 by 5 filtering window. The image is more blurred. So still, this one is not convenient. Maybe a 3 by 3 window is better because we have to make intact the number of pixels that we are considering. But maybe we have to change the content of that 3 by 3 pixels. Then if we run it, a better image than the previous one. But still, needs some improvement. So from this we can understand that for filtering to work, we have to have an optimal window size that we are applying. So experimentation is critical concerning what window size we have to use. Even we can add more noise into the image. To add more noise, we have different types of noises, like salt and pepper noise, speckle noise, periodic noise, Gaussian noise. Let's add the salt and pepper noise into the image. Still, how much noise we have to add is another issue. Can we corrupt the image by 18%? Or can we corrupt the image by 20%? Or can we corrupt the image by 15%? That one is dependent on our interest. If we corrupt the original image by 18%, almost most of the pixels are corrupted with salt and pepper noise. See the result. Almost the contents are readable. If you reduce into 0.08, says that 8% of the noises are enough to appear in our image. It's corrupted by salt and pepper noise, but still the content is readable. Then run the median filtering, which is better for especially the salt and pepper noise. We have to give it the graded image, which is J, after adding more noises of salt and pepper. And if you run the median filtering, those noises are removed. If we convert this image, the corrupted image, into binary, BW is equal to the IM noise, designing the image. Which is more optimized as compared to grayscale to binary. We are trying to design not the original image, rather the image which is corrupted with external noise. Already there are noises when we are designing it, since it is converting into monochrome image with 0 and 1. Almost it looks like the image is full of noise. Once we binarize it, what will happen if we apply the median filtering on the binarized image after adding noise? Almost those noises are removed that are corrupting the background. But still some noises that are not removed from the picture elements. Even at the end of, at the edge of the image, there are noises that are untouched. So we can also attempt to apply morphological analysis. For that, we need image erosion and image dilution. So image erode is trying to erode the image. So another last second. So if we use erode the image, That means it's trying to remove picture elements and magnify the background. We have already a binarized image, PW. And now when we are reloading it, using IM_ROAD, image road, we have to give it the original image and also window or structuring element. Our structuring element is H. Oh, it's expecting a structuring element which contains a binary format, zeros and one. So that means we have to create it again. B is equal to once a 3 by 3 structuring element. Given a structuring element 3 by 3, if we run IM_ROAD, so it tries to magnify those background pixels. In the meantime, if the foreground pixels are also corrupted with noise, it will also magnify them. So the major aim of erosion is trying to remove picture elements. Now, based on the IM_ROAD, if we dilute, what is the result that we get? That means, what if we magnify the foreground pixel? We use the same picture element B, but we are running it on the eroded image. So we have to change the picture element, or we have to first run dilution or erosion. Oh, there is a problem. We are displaying the results of erosion, not dilution, because the results of the dilution is saved in capital E. So when we are showing also, we have to give capital E. If we are giving it another value, it is trying to display the content of that value. D is containing the results of erosion. So when we are applying the dilution operator, since already the image is eroded, so we are getting by removing the background, that means by cleaning the background, it will give us the foreground. But the foreground is corrupted by the added salt and pepper, which is affecting the naturalness of the image. Resizing the image is also possible. Sometimes you may get an image with few number of pixels or an image with large number of pixels. If the picture is very small, we can enlarge it. If the picture is very large, we can reduce the size. For that, we need to apply IM resize. IM resize is trying to normalize the image as per our requirement, given the original image. Our original image is with this size. Now I want to make it double the size, the current size of the image. So then I am resize image multiple times. Then the size of the image will be enlarged. If you want to create a small size, you have to give it in decimal number. Like if I want to reduce the original image size by 15%, 0.5. The major thing is by defining the size of the image that we need. Accordingly, we can set the image size. So the project is also to explore the different image filtering techniques, then identify either one image filtering technique or a combination of them, such that we can attempt to improve the quality and the naturalness of the image. So back to our discussion of segmentation. If necessary, we'll come back to MATLAB in our next class. We said in our segmentation, given an image, if you apply region drawing segmentation, we have to define the point where we can start applying region drawing. That means we have to identify the seed point where the algorithm starts evaluating the nearby pixels and identify the subregions within the region. And the other is what kind of window we have to use for the evaluation to identify similar pixels. So either we can use for connectivity or aid connectivity. We can define cross, or we can define multiplication sign such that we can check the diagonal pixel, neighboring pixels, or the aid connectivity pixels. As the number of pixels considered increases, similar pixels that we are identifying also increases. So if you are identifying few number of subregions, it's better to use large window. But if you need to identify small subregions, it's better to use for connectivities or small window. So given the image and our seed point is the central pixel, and the issue of which pixels are similar, two pixels are similar if their difference is less than or equal to 5, our cutoff point. Then if you run using the 4 connectivity, the region grow, starting from the central pixel, 60, and in a 4 connectivity, we are trying to see the 4 directions, top, down, left, and right. So when you are looking at to the left of 60, the difference is 50, which is greater than our cutoff point 5. So it has to be ignored. Compare 16 with 64. The difference is less than 5. So 64 and the 16 are similar and they are representing the same subregion. Compare 16 and the 65, again less than or equal to 5. 65 is also describing the same subregion with 16. So we are taking 64, 16 and the 65 as one part of a subregion. But 10 and the 15 are not part of or are not similar with 16. 10 and the 17 should be ignored. Then we can go to 64 and again see the 4 connectivities. That means left direction, right direction, top of 64 and bottom of 64. So we have to see 16, 69, 59 and the 16. Which of the pixels are near to 64? If they are fulfilling our threshold value less than or equal to 5. 16 is similar with 64 because the difference is less than or equal to 5. 69 is also less than or equal to 5. So it's also similar with 64. 59, 9, the difference is 5 again. It is also similar with 64. 16 are already similar. So the region is growing. Now we started from 16, 65 is included, 64 is included, 16, 69 and 59 is included. Then again you have to go expanding by considering from 16 where can we go. The 4 C evaluates the 4 directions, but none of them are similar with 16 because they are not fulfilling the cutoff value less than or equal to 5. So here we reached to the end of the given subregion. But in this direction, we have to go 59. Then 56 is similar with 59 since the threshold value is fulfilled. 59, 17 already. 17 is also ignored by 60. And then now we have to ignore also when we are looking it from 59 because the difference is 11. 17 is also ignored. But 56 is included through 59. So now the 59, the region is growing to 56. But 17 is included when we are evaluating 17 along with 69. Because the difference between 69 and 17 is 1, less than or equal to 5. Even if it is far from 59, it is near to 69, so it should be part of the picture element. In such a way, these all those with red colors are part of the picture element. This is as per the 4 connectivity. What about 8 connectivity? More pixels are included. Because in 8 connectivity, we are not only looking at the cross, left, right, top and down, but also the diagonal lines. We are adding more 4 pixels for evaluation. So by looking around 60, diagonally in both directions, row wise and column wise, even when we are looking at diagonally, 59 is included, 16 is included, 59 is included, Only 67 is ignored when it's evaluating from 16. But 67 can be included when you are evaluating from the point of 65 and the 17. So again, window is critical for region group. We have selected the proper window size depending on what kind of sub-regions that we are looking for. If you are looking for more sub-regions, you have to minimize the connectivity. If you want only to differentiate between the foreground and the background, it's better to go for 8 connectivity. The other technique, which is well known in machine learning, clustering technique, which can help us to cluster the image into subregion based on pixel similarity. Clustering is basically trying to identify the natural groupings between different data elements. Here, for our case, it's trying to find the natural similarity between pixel element. Especially the k-means is also implemented in MATLAB. As you know, k-means, k is the number of clusters, the number of groups that we are expecting. In our case, the number of subregions that we are expecting from a given image. Mean is to define a centroid value for a given cluster. So the name k-means. If you know the number of subregions that you need, then using centroid value, which is calculated using mean, you can still identify the subregions using k-means clustering. How k-means works? Obviously, the first thing is we have to define the number of subregions that we need k. Then for each subregions, k1, k2, k3, we have to randomly assign the pixel values. Then see the similarity between the number of subregions that we need against the pixels. And then the pixels are categorized into the region where they are more near. Then we are doing these things until the centroid value stops changing. If the centroid value is changing, you have to go on rearranging the pixels that are clustered into a given subregion. But when the centroid stops running, then we got optimal subregions that are containing only pixels that are similar with each other. Again, clustering is a region-based segmentation because it's evaluating the subregions based on pixel similarity. There are many other algorithms available with edge-based segmentation.